Hello, everybody, and welcome to the SJAA July Imaging Special Interest Group meeting. I'm Paolo Barrettoni, and as you can see from my, let's say, name on the screen, I am filling for Mervate, that is our normal, usual, gracious host that is good for him in vacation. So tonight we will have again Alex Woronow, that is a new a member of the SJAA and is based in Tucson, Arizona, and is also a member for other group, but is so nice with us to share his knowledge about processing images. And tonight he will talk about a very interesting aspect of the narrowband processing, that is extracting the very precise band from the continuum that normally the window of the filter has. I'm sure that he will be better than me to describe everything. So please, Alex, go ahead.
Well, thank you. Okay, you should be seeing my screen. Yes. As Paolo said, I'm going to talk about extracting emission lines from RGB plus SHO image data. And this is my second talk in a row, and I'm really pleased that somebody came back to see it again. I hope there'll be something in here for everyone. I'm going to start out fairly elementary and work my way up. Let's see, I can't, it doesn't seem to be forwarding my slide though. That's not good. There we go. So let me see, I missed one slide here. So we're gonna go back, there we go. So ground up talk. We're gonna start with some easy stuff and work our way up into a couple of topics that are a little more advanced toward the end. So we're gonna talk about what are the emission lines we can capture and are worth capturing, and some of the motivations for capturing those lines. What can we do with them? And we're going to talk about what emission lines are and how they arise. Some pretty elementary physics that probably most of you already know, but we'll make sure everybody's on the same page. Then you're going to look at my equations for extracting the emission lines from the continuum background, which is always present in any image you capture, and the assumptions and requirements for making that line extraction, and extracting one line from a broadband image, for instance, extracting the O3 line in the blue, from the blue RGB image. And then there's a problem, in fact, of extracting two lines at once from a broadband image, such as hydrogen and sulfur, which both reside in the red broadband image. And so I'll look at the equations for those two cases. And then roughly, I'll quickly show you why the only published thing I can find on extracting lines was published by Paris and Lozano this year. And their equations, I think, are demonstrably inadequate or incorrect, and I'll show you why. I wrote a script that does my narrowband extractions, a PixInsight script, and it also puts together images, color images, using a true color mapping or something close to true color mapping. I'm a big advocate of not using the Hubble palette, which I find annoying and shocking to the eye, but that's a personal thing. Anyway, I'll show you the script and maybe work a little example, and then have a suggestion for something interesting that we might be able to do in the future in terms of extracting emission lines a little better than what I'm going to show. Okay, so where do we find emission lines, at least the ones we can observe? Emission lines come from common elements in the universe. So we don't find too many emission lines, if any, from uranium or things like that are very rare in the universe. Instead, we find them largely from chemical elements we're familiar with, and those that are in the human visible spectra are largely hydrogen, sulfur, and oxygen, those three strong ones that we can see. Hydrogen, there are actually two lines. One's called hydrogen alpha and the other hydrogen beta. And then there's sulfur S2 line and oxygen O3 line. And those Roman numerals indicate the number of electrons that have been knocked out of the orbit. It's one less than that. So O3 has lost 2 electrons. Emission lines, generally, for the stuff we can image, arise in turbulent interstellar clouds and at high temperatures. And these kind of environments are found in star-forming regions in those clouds, and sometimes when interstellar clouds are colliding. And sometimes the collisions are actually formed by the star formation itself. We can also find these emission lines, particularly the hydrogen and oxygen, in supernova remnants like the Ring Nebula and things like that. Some stars have emission lines. Most of them have absorption lines. Some have a few emission lines as well. And solar flares have emission lines, but I'm not going to talk about either the stars or the flares this evening, just really about the clouds. So here is an example of an SHO emission line image that I made for NGC 6357. It's a strongly emitting, strongly stimulated gas cloud, and the radiation is strong from that. And I pulled out the emission lines using my script and composed an image that's pretty close to true color for this image. I'll explain the true color part a little bit later. Not all clouds are emission nebula. Not all bright nebula are emission nebula. This is the Pleiades, and this is a reflection nebula. And it's actually just like the scattering in our sky. It's blue because of the light being scattered. The blue light is scattered with its shorter wavelength than the red light, which comes through more cleanly. In this case, it's kind of interesting. Those stars are considerable distance behind the cloud, and they're illuminating them from behind as the two pass in outer space. Okay, how do atomic emission lines arise? An electron is in an atom is kicked from a low energy orbital up to a higher energy orbital, or kicked totally out of the atom. This atom is then said to be in an excited state, and that's unstable. It wants to have that electron, and eventually, and the electron wants to be in the atom. So eventually the electron resumes its ground state. So it moves from an excited state, perhaps free around the atom, to the ground state of the atom. And as it does so, it releases energy, and that energy is in the form of a photon. And the energy or wavelength of the photon, it depends on how large the transition was. Was it in all the way into the ground state of the atom, or was it part way down? And we'll show a little bit of that in the next slide. So there's two ways that we generally think of as the prominent ways anyway of stimulating an electron in an atom. And the first way is by having a photon hit the electron. And if the photon's energy, its wavelength, is the energy difference between this inner orbital of the atom, this is the nucleus, and the upper orbital, then this electron will be knocked into an upper orbital, just like this. And that's an excited state of the atom then. Well, that leaves this orbital empty, and it's lower energy, and everything seeks a lower energy, it seems. So this electron is going to try to get back to the lower state, and we'll show that in a minute. There's also collisions. We take these two atoms here and we slam them together. There's a chance that the energy of that collision is enough to kick at least one of those electrons from the atom to a higher energy state. And then either this case or this case, we end up with an excited atom. That photon, that atom, I'm sorry, that electron wants to get back. And when it does so, it emits a photon equal to the energy difference between these two states. And if we look at this diagram down here, it shows what an electron around a hydrogen atom nucleus can do. And probably the most prominent one where these are a bunch of series which are based on where the atom ends up after it cascades or jumps to a lower energy state. There's the Lyman, the Paschen, and the Balmer series. And the Balmer series is our most common one. And the Balmer series is where it comes down to the N2, the second orbital. And this one right here, this jump from the fourth orbital down to the second orbital, is the one that emits hydrogen alpha. So it's this process of exciting an atom through a collision, perhaps in a shock wave, or through heat, which jars the atoms together. They rattle together and the electron jumps up, or through absorbing a photon. Okay, that's the emission lines, and they're shown down here in this diagram. Here's hydrogen alpha. And this line here, this set of observations in this spectra here, is the continuum. And you see it doesn't sit at zero. So when we observe a hydrogen alpha line, we observe everything between a wavelength here and a wavelength here. So that includes not only the line, but all of this continuum, which isn't very interesting to us. It has nothing to do with the physical processes in the cloud directly, at least not as directly as the emission lines do. So that's hydrogen alpha. There's hydrogen beta. There's oxygen 3. What else did we want? Sulfur 2 over here, singly ionized sulfur. Okay. Interestingly, there are many things that cause this background here, this continuum of radiation. It's very often black body radiation, which maybe you studied in school, which is just a mix of transitions going on, emitting photons, free transitions where electrons are free in a matrix, in the gas matrix, and pass by atoms and change their energy as they interact with the atoms around them. Molecular vibrations and molecular rotations also cause the background radiation. Interestingly, the molecular vibrations are called phonons, not photons, but phonons. And that term I knew, but in researching for this talk, I found out that the rotations of molecules are called, or the energy differences in rotations that spawn light are called rotons. Isn't that interesting? Crossword puzzle. Anyhow, here's a spectrum, the one I showed before, last one with the continuum down here. And here's the radiation of a star, whatever it is, V1150 TARS. And you see here, the background radiation looks like this. And this is typical black body continuum radiation. This is probably black body too. I'm not absolutely sure, but it looks like black body radiation, just at a much lower temperature. As temperature increases, this curve gets more peaked and higher and more compressed to the left. Let's see. These were taken by an amateur with spectrums. Now, what's a narrow band versus a broad band image? We're going to use both of them to extract our emission line. Broadband images, as you probably know, use filters that are about 100 nanometers in width. And the common ones we use are L, RGB, luminance, red, green, and blue. I'm not going to talk about the luminance, but we will talk about RG and B. Excuse me. Narrowband images center around these emission lines, and they usually have widths between 3 and 10 nanometers. And of course, they emit far less light, and most times they take considerably longer exposure than the RGB ones, which emit more light, being wider bandwidth. So here's some astronomique filters just to show what we're talking about. So each of these filters is somewhere around 100 nanometers in width, and the red, green, and blue. Red ones in this case, green ones in this case overlap with the blue a little bit. And unfortunately, the O emission line lies right in here somewhere. Narrowband filters are, as you can see, these are on the same scale. Narrowband filter is obviously much more peaked and tries to just isolate one of the bands. But you'll also notice that these broadband filters span a range where, for instance, the red one contains not only red, but a little bit of orange. And the green filter contains a little yellow, and the blue contains some violet. So they're not just pure red, green, and blue as we often treat them. And on a side story a little bit, I guess, is this diagram. This shows the color range of various things. Let's just leave it at things for a second. Here's the human eye in this horseshoe-shaped thing. This is what we can perceive. If you have good eyes and good color reception, you should be able to see this range of colors. Your monitor, on the other hand, follows this little triangle right in here, the sRGB triangle. When you're processing your images, you can choose to process them in something like Adobe RGB or ProPhoto RGB, which are much larger triangles and therefore have more colors available to you. The problem is when you display them on your monitor or anybody else displays them on their monitor, they're going to see sRGB. I don't know of any monitors that cover all of the Adobe RGB and none that cover ProPhoto. So if you're making images to share with somebody, eventually you're going to end up in sRGB, whether by your own hand or by that of the manufacturer of your display screen or by AstroBin or whatever. But that's just, notice also that we're rather depleted in green compared to our depletion of red and blue if we use the sRGB. And that's fine for astro imaging because there's just not that much out there that's truly green in color. But if you're doing trees and forests and things like that, it's kind of a shame we don't get more of the greens, but we don't. Okay. The utility of emission lines. If I'm going to extract these things, what is it I'm going to do with them? Well, one thing is make pretty pictures, and I guess that's covered down here. It makes things, the images more complex, detailed, interesting, and in some degree informative. It adds textures, shapes, and details, or at least it might. You're liable to extract all the things, all the narrowband emission lines, and still come up with an image that's just kind of a flat white, flat red thing, for instance. And it allows you to better adjust dynamic ranges, tones, and saturations. Scientifically, it tells scientists, if you use something like the Hubble palette, it tells the locations, proximities, and geometries of the active areas in the nebula, the areas where stars are forming perhaps, or where clouds are colliding. This obviously is something of interest to professional astronomers. It reveals the proportions of hydrogen, oxygen, and sulfur in the regions to some degree. If you have red areas and blue areas, you can, and if you're using a Hubble palette, red, green, and blue areas. then this would show you the distribution of these chemical elements in this space. However, I suspect that a professional who wants to know that would take a spectrogram of the area and find it out rather than taking a set of narrowband images. And I just found out today that the hydrogen alpha O3 ratio in planetary nebula is heightened, increases in areas of bow shocks. So tomorrow I will start on an image to see if I can see bow shocks in a planetary nebula. But just learned that this afternoon. Okay, here's another emission line example I did. And this is mapped in true color, which I'm going to talk about in a little bit. But we're moving into the color thing fast. For those of you who like Futurama, and there was a period in my life when I did, there's an episode called Prisoner of Benda, and that's when the professor, this is a cartoon by the way, when the professor gets caught in Bender's body and they're trying to figure out how to get him back into his own body. And there's a phrase that says, I'm afraid we'll have to use math. And so we're gonna have to use some math coming up here real fast. By the way, the guy who wrote this holds one of the writers for Futurama holds a PhD in applied mathematics. And there's actually now a mathematical theorem out there based on this episode here, The Prisoner of Benda. So who knows where math is going these days. Anyway, here's my method of extracting the emission lines. Say we want to extract the green line, the green O3 portion of the green O3 line from broadband and narrowband images, a G in the broadband and the O3 narrowband images. We can write two simultaneous equations for the flux recorded by those two images. And if we write it, if we take B as the broadband and N as the narrowband, let's start by writing the equation for the broadband. Very simply, it's the line, the emission line, plus the continuum equals the total flux that we record in B. Whereas in the narrowband line, what we want to do is scale it to the same thing. So it's the narrowband line has the same emission line, but the exposure E sub N divided by E sub B, the narrowband divided by the broadband exposures scales how much of the flux we can attribute to L. And if we make that same ratio to scale C, we also need to scale it by the width of the two filters, the narrowband being, say, 10, the narrowband being 10 nanometers and the broadband being perhaps 100 nanometers. So now we have two simultaneous equations. We know all the E's, we know the W's. The two unknowns are the line and the continuum, and we very simply solve them for the line, and we get that the line is equal to the narrowband minus A times B. B is the broadband image. A is this ratio, this set of constants, divided by so this is what happens when you get old. All of a sudden things go out of your mind. By E sub N divided by E sub B minus, again, this constant. This is the exposures. There we go, came back. Okay, now the problem is if we look at our narrowband red image, broadband red image, it contains two emission lines in it, the hydrogen alpha and the sulfur 2 lines. So we have to write three equations. And they look just like the equations we just wrote, except there are much more complicated contortions of all the constants being multiplied and divided. And so instead, I just simply write it in a simple matrix form, linear, and solve these linear equations for N1 and N2, where N1 might be the hydrogen alpha line and N2 being the sulfur 2 line. So this is very easy to solve, and you get both the hydrogen and the sulfur out in one pass. I should say one other thing. I have a script which I will make available on our website sometime this week, and I have a complete write-up that goes through pretty much all of this and explains it a little better than I'm probably doing tonight on the fly. Anyway, the underlying assumptions for these equations I just presented, which are easily solved, is that the continuum flux per unit wavelength of the broadband image is the same as that same continuum flux in the narrowband image. If you remember back several slides where I showed the emission spectrum of a nebula and pointed out the continuum, it was fairly flat. And so over a 100 versus a 10 nanometer section, the broadband versus narrowband, that assumption is probably fairly good. Not perfect, but probably closer than we would expect or intuitively expect, perhaps. The other assumption, number 2, is that the filter transmission efficiencies is the same for the broadband and the narrowband image. If there isn't, we can introduce another factor into there, the ratio of the efficiencies, and solve that. But most modern filters, both broadband and narrowband, are pretty efficient, almost always above 95% efficient, and often above 98%. And finally, that when processing them, you have to check and make sure that your narrowband and broadband images don't have a pedestal. If they do, the equations don't hold, but if they do, simply remove that pedestal before you do the calculations. Okay, now Paris and Lozano this year published an equation which they called something like continuum subtraction, which I took it, and I think everybody else did, to mean that it's going to give you the emission line. And this is their equation. They don't put emission line on the left side of the equation, they just give you the right-hand side. So this is what I presume they're solving for. The equation is you take the HA, that's the narrowband filter, and you subtract the quantity, the broadband red filter minus the median value of that red. Remember, a median is the midpoint in terms of 50 percentile. Half the values in the red filter are below that and half are above. And then you hunt around, make some tests, and find a value of K that makes the image look the way you think it should. And you multiply that thing in the parentheses here by that K. So I'd like to point out something. This half the time, when R is less than the median, that's half the time. This is a negative value multiplied by a positive value, so it's still a negative value, and subtract it from HA, and so you're adding something to the hydrogen alpha. If this is continuum subtraction, what is it you're adding to the hydrogen alpha? It can't be anything. On the other hand, if R is less than the median, then this is a negative number. Is that what I just did? If R is greater than the median, then this is a positive number multiplied by a positive number is a positive number, and you subtract it from hydrogen alpha, and it seems like you're subtracting something. Perhaps it's the continuum. I don't know any physics that says that this thing here is the physics of the continuum. The equations I showed you just a little while are based on simple physical principles. This one is just ad hoc. All it's doing is emphasizing the areas that have more red already and de-emphasizing the areas that have less red. And besides which, if you have a nebula that only makes up part of the image, the median value of all the nebula may be above the median value across the entire image, which is what this median is. So I'm not happy with that equation, especially when mine are so easy to use, in fact, and so obvious. Okay, finally, here's my narrowband assistant. I call it my app script in PixInsight for doing these calculations. It's pretty simple to use. You just select your broadband images for these spots. They're narrowband images for these. There's a HA boost factor. How much of that red HA subtracted from found in the emission line, how much emission line do you want to add back into the red part of your image? How much red from the S2 and true color do you want to add in? And how much do you want to boost the blue and green from the O? And you can adjust these, you can leave them at 1. You can play with them any way you want. And it also calculates an HB, hydrogen beta emission, where you have hydrogen alpha and nebula. You virtually always have a proportion of that equals the hydrogen beta, and it's around 35%, the default here. So that gives you a little bit of blue too. You input information about your narrowband filters, the widths of the filters, and the broadband filter size, and these are the narrowband filters, and then the exposures of the broadband and the exposures of the narrowband filters. You can, if you push this value around, there's going to be parts of your image. For instance, all of these narrowband images it's going to extract a hydrogen, sulfur, and oxygen line. And those lines those images will tend to have black holes in them, areas where there was no HA recorded or sulfur recorded, etc. And if you push this line up, you can plug those areas by warping the equations a bit. Whether you want to warp the equations or not, it's up to you. If you leave it at 1, there's no warping. And the images that come out, as I said, are the 3 narrowband images. It also makes a SJAA RGB image according to the mixtures that you specified up here. And it makes an SHO image with the true color mapping. Both these are what I call true color mapping. Okay, now most narrowband images, if you're a devotee of Astrobin, you find that most SHO images use the Hubble palette. In the Hubble palette, sulfur is red, hydrogen is green, and oxygen is blue. This is called an ordered coloring or ordered palette, because this is the longest wavelength, less long, and shortest wavelength. As I said earlier, professionals may like this because it tells them something about the distribution of the chemical species. I am not looking at the distribution of the chemical species, and I don't expect any professional scientists working with Hubble images or what have you to go out on Astrobin and search down my images for them to do their science. They're going to use telescopes of several orders of magnitude more power. So I do mine for art, for satisfying visual images. And I do not find the Hubble palette to create satisfying color images. Furthermore, the star colors are distorted in the Hubble palette. They're usually magenta by the time you're done with it. Some people take RGB and paste the RGB stars in place of these magenta stars. And some others simply use a star mask and remove the color totally from those stars. Other observatories, by the way, use other one-to-one SHO mapping color palettes besides the Hubble palette. And those seem not to get very much playtime on Astrobin. So here's my mapping. And I remind you where the spectrum is. The shortest wavelength is sulfur. So I make sulfur red. I say the intensity of the sulfur image is equal to the red image. So when I'm mixing RGB, that one's red. The HA is somewhat longer wavelength, shorter wavelength. I don't know. Yeah, shorter wavelength than that. So it's off toward the green just a bit. It's rather arbitrary, but I said I make my HA 70% green and 83% red. That puts it in the right place, more or less right place relative to the sulfur. O lies out here in the blue-green, and I mix it at 39% green and 61% red. And then I make up this hydrogen beta, which I told you about earlier, because where there's a hydrogen alpha, there's hydrogen beta. And so I assign the flux at 35% of the hydrogen alpha flux. You can change that if you want, and make it 0 or any other number. And I set it at 20% green and 80% blue. Eventually, in probably the next edition of my script, these equations will be adjustable to user discretion. Right now, they're hardwired in. Okay, the advantages of this true color mapping is you can use photometric color calibration from PixInsight on it. And when you do that, the stars aren't shifted a great deal. They're usually shifted somewhat, just like they are in your RGB images. And if you don't like that, then you don't have to go through with the color calibration, or you can isolate the stars and color them yourself. Whatever was available to you with RGB is available here too. You can display your images at home or in public without having to try to explain what all the funny green things are in there, green areas and what have you. As I said, eventually these will be adjustable. Okay. Now the images that you can output depends on right now on the images that you input. For instance, if you input just HA, S, and O, and maybe these aren't the lines, maybe these are just the raw stacks that you have, but it'll produce an SHO true color image for you. If you put in HA and RGB, or O and RGB, or S and RGB, it'll help put in an HRGB image and the H line, or sRGB and S line, or whatever you have. If you put in the whole kit and caboodle here, hydrogen, sulfur, oxygen, and RGB, you get out an SRO RGB and HSO image, both these being true color, and all three of the lines. What else? If you want to iterate, you can check a box here, and it will leave everything untouched in your setup, and you can, when it reinitializes, and you can move sliders around or adjust whatever it is you would like to adjust. Okay, I'd like to go to a live example. Let's see if I can make that work. Let's go there. PixInsight. Okay, I have here a image data for NGC 3557, and it is taken on a plane wave 17-inch by Deep Sky West, which is a place where you can purchase subscriptions to telescopes, and it was taken in Chile. I have here my program, Narrowband Assistant, and when I open it up, because I prepared already, we have the R, G, and B filled in, the H, S, and O. Here are the individual images. Take that down for a minute. So if you look at, for instance, the H image, oops, that's clicked in the wrong place on that. There's the H, what the H image looks like. So these are all black and white standard stacks of images. Okay, back to this one. So those are all filled in. I'm going to leave the default values in here. My broadband filter was about, for this telescope, was about 100 nanometers. The narrow bands were 8 nanometers. There was a 900 second exposure for the broadband images and 1800 for the O exposures. I'm not going to screw with that value. I'm going to make all of the images possible, all 3 lines and the 2 combined images. So all you do is take a deep breath and hope and push run. And it starts, most of these images will be deleted. They're intermediate images where it's getting scaling. It's also doing linear fitting to the images, which takes most of the time in here. So what it's doing right now is linear fit, going down to the end. Okay, and it's done. And so here is the line image. This is SHO image in true color. Here you see these scars where there was no narrow band around these stars. This is very common effect. If I take that slider and go back and slide slide this cosmetic slider up to maybe 1.5, all of those will go away. And the problem is at that point, we're introducing some of the broadband image back into the narrowband image. And here is the RGBSHO image. And this long thing here tells you that, for instance, sulfur is in there at a slider value of 1, hydrogen at 1, oxygen at 1, and then there's RGB. And so again, this is true color. Obviously, there needs to be some cropping done here on the side, but the star colors are pretty reasonable. It's a little harder to see the star colors in this one, unfortunately, because stars don't come out real well in narrowband images, but they're also close, but the intensity of this one needs to be boosted. The saturation clearly needs to be boosted. Okay, in addition to those, we have 4 lines, believe it or not. Here's the hydrogen alpha line that was extracted. This is just the line without the continuum in it. Here's the O extracted from the blue broadband image. So this is the blue component of the oxygen. Here's the green component of the oxygen. The images are not totally identical, especially in intensity, which is interesting. I don't think anybody has taken the effort to extract them from both those, as you should, and then you combine them back into one line, ultimately, when you use it. And this is the sulfur line. What I didn't extract, didn't show, is the hydrogen beta line, but the hydrogen beta would be just this image if you multiplied every pixel by 0.35 and then add it into the blue rather than into the red somewhere. So that's how the thing works. And I'm so glad it actually worked. Okay, some possible additions, color mapping, as I said, so that the user can adjust the color mapping to true color or any other thing they want to do, and increase the flexibility of the inputs such that you could just input R and HA and get out the HA line. Right now, you have to put in all the RGB and HA to get it out. That's just kind of a limitation that's easily remedied. Here's my idea for the future to get a better estimate still of the narrowband images. What if we, rather than using broadband and narrowband, use 2 narrowband and took an image at 5 nanometers and 3 nanometers? This would have really helped in making sure that the continuum value is common between those two, or extremely close to being common between those two. So I've never seen this done, but if you happen to have a couple extra sets of narrowband filters lying around, perhaps you started out with 10 nanometers and decided to go to 5 or to 3, you might give that a try and see if it works using the equations, same equations I have. Another advantage of this is it would isolate just the hydrogen, and you wouldn't have to simultaneously extract the hydrogen and the sulfur, which must add a little bit of uncertainty to the images that come out. Okay, I think that's all I have today. Here's an image. That's the true line version. Here's the RGB version. This has been processed, and the pre-processing was all done in PixInsight. Most of the post-processing was done in Topaz, various ones, and in Aurora HDR. And I think that's the last slide I have. It is. So I'd be happy to answer any questions or whatever you got going for you. I'll unshare my screen here.
Thank you. Thank you, Alex. And let me start with a question that I noted here. I noted that you use always very, very good subs. I mean, the data set are normally coming from a real good telescope and location. What, let's say, is the influence of a, let's say, less than stellar, let me pun intended, data set, or I mean, the data set that the commoner like us can produce in our backyard in that approach?
I think one of the keys is always going to be suppressing noise. And one thing that can be done is to operate in some way to suppress noise in your unstretched. All this, of course, is the mathematics are all for unstretched images. So you have to suppress the noise in the images before you apply these mathematical tools as best you can. One thing, of course, we have at our command is more exposures. And with these telescopes, I'm working with about 3 or 4 hours of SHO under very good skies. I don't have any problem. Under skies here in Tucson, metropolitan area, it would be much more difficult. I really just don't have any personal experience with it, but it's all going to be about noise. I guess if you really think about it, you're carrying the noise through, so some noise suppression after the fact is important too. I usually hit noise pretty hard. There's now a new AI noise tool. What is it called? Available within PixInsight. It costs a few bucks.
Noise exterminator.
Noise exterminator. I use that one occasionally, mostly not. Most of my noise suppression is done after stretching, and I use Topaz denoise, which is very flexible. And when you get used to using it, it's very effective at removing noise and not much else. That's the best I guess I can do is try it and see and be aware. Maybe whatever's called Murray or Mura noise suppression would work. I never use that one's done on subs right after stacking.
One other thought about your last note about the possibility to combine different windows in narrowband in terms of filter, so different window size. And I was thinking to the approach that Francesco had with a multiple location and people contributing to the same image. That is an approach can be used in that case. I mean, you have to scale probably from one image to the other. So the pixel size has been different.
That I'm not quite sure what starts to happen as pixel sizes get different. I think that's not a huge problem because, of course, whether you're downscaling the pixels or whether you're aligning subs, you're interpolating all the time. And, if you dithered your subs, you're interpolating. And that's what you would be doing if you were taking images of different sizes from different scopes anyway. And of course, collaboration, as you suggest, maybe one person has one bandwidth of narrowband filters and another person has the other. And trading the data would be a less expensive than buying two sets of filters.
Also, because a carousel with 20 filters is not an easy one.
That's true. Yeah.
We need to get there. The JWST has like 15 filters or something like that.
Oh, yeah.
One thing that it's not for me because I had the good chance of getting a pre-release of the script, but is there a URL that can be maybe shared in the chat where people can download your script?
Yeah, I don't have I have a Dropbox address, and maybe what I can do is just post that sometime later this week, and I'll fix up, make it the most recent version and post the Dropbox link where you can download it.
Thanks.
Okay, and maybe I will do a broadcast on the group to alert everybody that the script is available.
Okay, yeah. Yeah, and if at any time, of course, you have questions or suggestions for improving the script or what it's actually doing, let me know. It only took me 6 months to write that 1,000 lines. So.
Okay, so if there is no other further question, we can first of all thank you and to Alex for a lot of food for thought, and thank you everybody for participating. And I'm
actually. I have one last question, sir.
Sure.
Alex, wonderful presentation, really enjoyed it. Is it possible to share the presentation itself? There was a lot of stuff, quite intricate, and it would be helpful for newbies like me to go over it probably multiple times to understand.
Okay, well, I believe this was recorded, so it could be published that way. I will also put in that same Dropbox my view graphs.
Okay, sounds good.
Yeah, I confirm that is recorded and will be available in few days. Glenn will take care of processing the things.
Okay, thank you very much.
Sure.
So, okay. Thank you again. Thank you, Alex. And that's conclude the July meeting.
Thank you.
Bye.
Bye-bye.
Thank you very much.
Thank you.
Thank you.
Bye.